Hello, in this video we are going to study about stack organization. What are stacks? A stack is a storage device that stores information in such a manner that the item stored last is the first item retrieved. It uses the concept of last in first out. So a stack is essentially a memory unit along with an address register that can only count. A register that holds the address of the stack is called stack pointer. So this stack pointer SP holds the address of the stack. There are two operations in stack: push and pop. Push means we are inserting something into the stack, and pop means we are removing the item from the top of the stack. Push is simulated by incrementing the SP register, and pop is simulated by decrementing the SP register. There are two types of stacks: register stacks and the memory stacks. If a stack is placed into a portion of large memory, it is known as memory stack, and if it is used in the memory words or the registers, it is known as the register stack. In this figure, there is a 64-word register stack numbered from 0 to 63. The first element is inserted at location 1 and top of the stack is given by stack pointer. So SP contains a binary number whose value is equal to the address of the word that is currently on the top of the stack. In this case, my SP is pointing to 3. To remove the top item, the memory word at address 3 is read and the content of SP is decremented. So if I do the pop operation, this C will be removed from this stack. SP will point to B. To add new item to the stack, SP is incremented. So when I want to add a new value, suppose I want to add D here, so what I will do, I will increment my SP by 1. It will be pointing to 4. So that will be my new SP. If I pop, then my SP will be SP equal to SP minus 1 in this case. So SP will be 2. So the first element is stored at location 1, and when I want to check how many values are there in the stack, there are total 64 locations, so there can be maximum of 64 values. So 0 to 63 means it has 64 locations, and the maximum value is 63, so it can be represented by 6 ones. When 63 is incremented by 1, then it will become 0. Why? Because when I add 1 to 111 111, it will become 1 and then 6 zeros, but my capacity is only of 6 bits. My SP is having a size of 6 bits because of a 64-word stack. Hence, this one will be discarded and SP will be back to 0. Similarly, if my SP is 0000000, it is decremented by 1, my SP will result into 111111. The 1-bit register full. My full register is a 1-bit register. It will hold the value 1 when the stack is full, and empty EMTY is set to 1 when stack is empty. When an item is read out from the stack, it is not actually physically removed from the memory, but that C value which is popped already, it is overwritten. This is overwritten by some new value. Now let's see push. For push, initially SP is cleared to 0, so my SP is having value of 0. empty is set to 1 and full is set to 0. So initially my stack is empty. When my stack is empty, so empty will be 1 and full will be 0 and sp will be 0 because this is my initial location. So when I want to push, I will not push at this 0 location, but I will push at 1 location. So this 1 location is filled as the first element of the stack. Now if the stack is not full, then a new item is inserted with a push operation, which is implemented using the following micro operation. Initially we will be doing sp equal to sp plus 1, so this 0 will be becoming 1, it will be incremented by 1, and the data register value is put into the MSP. This memory location is filled with value of dr. If my sp is 0, then full equal to 1. So what happens is, now here are two cases. If my stack is empty and I want to fill first value at location 1, at that moment sp was 0 and I have made it sp equal to sp plus 1. But as my stack fills up, this is 1, 2, 3 and this stack is filled up, and then the sp plus 1 is calculated, then my sp plus 1 will be in this case 0. So the final element will be at this location only. So this means if my sp is 0, this stack can be full, and if it is full, it is not empty. Now what does this mean? If sp is equal to 0, the first item stored in the stack is at address 1, which I told you, and the last item is stored at address 0. This happens when the second last item is stored at address 63. So in this case, when my top element was 63 location, this was the second last value, and after this something new came up and we stored it here. Now my stack is full. When 0 location is filled, my stack is full. It means this. Pop operation. Pop means item is deleted from the stack if the stack is not empty. If empty is equal to 0, then only pop is possible. So what happens? The top of the stack value is sent to dr, data register. sp is equal to sp minus 1. So this was my stack. I want to remove this part, so it has value 5, and suppose this was location 4. So my sp was 4 and I want to remove this, I want to pop this, so I will put this 5 at dr, and then I will decrease my sp to 3 because my new top of the stack is location 3. So sp equal to 4 minus 1, which is 3. If sp is equal to 0, then empty equal to 1. Now I told you that first value of the stack is filled at this location, at one location. Now after popping multiple times, it will be a condition when you will reach here, and when you will pop this, you will come to this 0. Now when sp is equal to 0, then stack is empty. If my first element of the stack is gone, it means all others are also gone. So my stack is empty, and full not equal to 0. So my stack is not full, but it is empty in case of pop. Now if we want to start popping items from a 64 word stack that is full, the first item is read from which address? So this is a stack. So this is my 63, this is my 0, 1, 2, and so on. So my stack is full, so everything is filled in here. I want to start popping. So from which location it will be starting? Because my last value was filled at 0 location, so this location will be popped first. So M0 will be popped into DR as the first element to be popped, and the second item to be popped is when we will be decreasing this SP 0 minus 1, so we will reach this value 63. So my value of 63 is the second item to be popped. Now if SP is equal to 0, is my stack full or empty? So my SP is pointing at this place. Now it depends. If you are coming from push and you are reaching SP at 0, then my stack is full. If I am coming from pop and I am reaching 0, then my stack is empty. I hope you know this. We have discussed already. If I am popping elements, I am coming downwards, and after I pop the location 1 element, I reach at 0. So in case of pop, when SP is equal to 0, my stack is empty. But in case of push, if I am pushing something, I am putting content here, and I am reaching at the top of the stack somewhere here, and then again I am pushing, I reach here. In that case my stack is full. So only saying my SP is equal to 0, we can't say stack is full or empty. It depends on push and pop. If we are doing push, my stack will be full on reaching SP equal to 0. If I am doing pop, my stack will be empty after reaching this location. Important note, if the stack is pushed when full equal to 1, so my stack is already full, or my stack is already empty. In case of full, you cannot push anymore. In case of empty, you cannot pop anymore. So that will be having some error. Memory stacks. We just saw register stacks. Now we will be seeing the memory stacks. So a stack can exist as a standalone unit, or it can be implemented in RAM attached to the CPU. In the CPU, a stack is implemented by assigning a portion of the memory to a stack operation and using a processor register as a stack pointer. So what does this mean? In a memory, suppose we say this is my RAM, some part of my RAM will be stack. It will be dedicated to stack. So in a computer memory with program, data and stack segment, this is my program segment, this is my data segment, and this is my stack segment. This full location from 4001 to 3000, whole of this is a stack. My current SP is at 3998, pointing to C, which is the top of the stack. So PC is to point the next instruction in the program. AR is used for pointing to an array of data. So AR will be pointing to the array of data, and program counter will be pointing to the next instruction on the program, and SP will be pointing to the top of the stack. My DR will be the data register holding the value. Now all three registers PC, AR and SP are connected to common address bus, and either one can provide an address for memory. Now PC is used during the fetch phase, AR is used during the execution phase, and SP is used during the push or pop items from the stack. In this figure, my stack grows from 4001 to 3000, and my first element is saved at location 4000, then 3999, then 3998, then 3997, and so on up to 3000. In this case, stack limit checks are not available. Now, only one way is there to know that my stack is full or empty. To check the stack limits, we have to save these two values using two registers. Two extra registers will be used to check these limits of stack. Otherwise, what will happen is, when we will be pushing the elements, might be that my stack overflows to 999 location. We don't want that, so this limit is to be checked using two registers, suppose R1 and suppose this one is R2. In memory, while doing the push operation, SP is equal to SP minus 1, so my 4000 was taken to 3999 while pushing, and then my DR value will be pushed into the memory location MSP at memory location of 3999. This DR value will be sent. Similarly, in pop operation, the top of the stack value will be sent into the data register and SP will be SP plus 1. So if I pop 3999 location value, this will be gone to DR and my SP will point back to 4000. Overflow and underflow. To check that my stack has overflow or underflow, I told you that we can use upper limit register and the lower limit register, which I told was R1 and R2. Advantage of memory stacks. A CPU can refer to a memory stack without having to specify an address, because the address is always available and updated automatically in the stack pointer. Now CPU can use that stack address from the memory by default, so we do not have to specify an address, because some part of it was stack and it was all part of RAM. So this stack is part of RAM and memory can be accessed easily, so we do not have to specifically give the address. Important note regarding the memory stacks: memory access through SP and updation of SP. What does this mean? For pushing and popping, these two things have to be done. We have to update the SP and we have to do the memory access using the SP. But the sequence matters on the organization of the stack. It depends upon how my stack is growing. Maybe my stack is growing downwards or my stack is growing upwards. Now in this organization 1, my stack is growing upwards. My addresses are decreasing with every push and it will reach up to 3000. The initial value of SP is deciding to which direction my stack is growing. In this organization 2, my initial SP is 3000 and it will be +1 every time for the push. So SP is SP plus 1 when I push. So it all depends upon the organization, how my stack is built. Reverse Polish notation. Now stacks are very useful for evaluating the arithmetic expressions, but my arithmetic expressions are commonly written in infix notation. What is infix notation? That operator is between two operands. This one, A and B, are two operands. Star is the operator here. So for this calculation, directly computer cannot do. There is a problem because how do we do it? We first multiply a into b, and then we multiply c into d, then we do the sum. Now this cannot be done directly using the infix notation. To solve this problem, we have prefix and postfix notations. When arithmetic expression in infix notation is converted to prefix or the postfix notation, the process simplifies. So we do not have to check back and forth the entire expression for determining which operation is to be performed. So what are Polish notation and reverse Polish notation? A plus b is infix notation, but if I take this operator before both the operands, in this case plus is ahead of ab, so this is known as Polish notation or prefix notation. Similarly, if I take this plus on the right side, this is known as reverse Polish notation or postfix notation. So this a into b plus c into d, when written as this, ab multiply, cd multiply and plus, so this is reverse Polish notation or the postfix notation for this expression, if this expression is e. Now how is the evaluation done? The expression is this one. It can be evaluated as follows. Scan the entire expression from left to right. When an operator is reached, perform the operation with the two operands found on the left side of the operator. So when I am scanning this from left to right, this star comes up, then I will solve this part first. I will do a into b, I will solve this, and I will be replacing the answer with a number obtained from the result. So suppose this was 5 into 6, so this will be 30, so this will replace 5 and 6 will be replaced by 30. In other words, we can say 5 6 star can be written as 30. Now the next numbers came up, 2 and 3, and then again multiply. So what will happen? This multiply will be used in 2 into 3. So this 2 and 3 will be multiplied and answer will be replaced by 6. So when both the operations are done, we can use this plus for 30 and 6. So the answer will be 36. Let's see the conversion algorithm. Scan the infix string character by character from left to right. Initialize an operand stack. So there will be two stacks. One will be operand stack and other will be the operator stack. So suppose I want to use a into b, so it will be a when I go from left to right, then star came up, I will put this star here, and then b came up, I will put this here. So this is how it's done. Initialize an operand stack. So my operand stack is initialized by a on the first element. Now what to do next? If the scanned character is an operand, so suppose it was b directly, but it was not b directly, it was multiply, so it was an operator. So what will we do? If there is an operator or a starting bracket symbol and stack is empty, then push it to the stack. So in case it was this, what to do? This is the operator stack, this is the operand stack. So first a came up, I have put into the operand stack, then operator came, then the star came up, it is put here, it is put into the operator stack. An operator and stack is not empty. So if there was some operator and my operator stack was not empty, then I would have checked for the precedence. Suppose plus has came up after A into B. I want to do C into D also. So after multiplication and after this B putting here, this plus came up. Now this is the case. Operator has come and stack is not empty because star was already there. We will compare the precedence. If stack top has higher or equal precedence, pop the stack. Now star is having higher precedence than plus, so this star will be pulled out. So this will be popped, and this one will be, and this AB will be becoming AB multiply, and then plus will be put here because of the second operator. Else push character to the stack. This else push character to the stack means if after plus another multiply comes up, now multiply is having higher precedence than plus, so this plus will be not be popped out. So this plus will not be popped out, and star will be pushed here. So this plus will be plus multiply after pushing the star. We have to repeat these points based on what comes up. Is it a bracket? Is it a multiply? Is it a plus? Is it a operand? So we have to take care of all the cases. If there is a closing bracket, then we have to pop the stack till the starting bracket is encountered. So if there is a operator like this was my operator stack, and then this bracket came up. After crossing B, this bracket came up. So when I want to put this bracket into the stack, it has to be used for popping all the elements till this starting bracket comes up. So this star will be popped out, and it will be AB star in this case. So after this star being popped out, it will become AB star. AB will be AB star. Add all the popped characters to the postfix string. So whichever characters are there between this and this, so all the operators will come here one by one. So it will be plus multiply, so everything will be popped out. So repeat the step 2 until all the characters have been scanned, and pop all the remaining operands from the stack. Add them to the postfix string. So let's see an example. So if there is A into B plus C into D, this is the infix expression given. So what we want to do, we scan it from left to right. So A comes up, A is put into the postfix string. Star comes up, so star is put into the operator stack. So I told you that one is the operand stack and other is the operator stack. So that operand stack is nothing but postfix string only. So when star comes up, it is put into the operator stack. Then the third character is scanned. This bracket, round bracket, it is put here into the operator stack. When B comes up, B is pushed into the postfix string. When plus comes up, plus is pushed into the operator stack. C comes up, C is pushed into the postfix string. Then the round bracket comes up. So when this bracket comes up, we have to scan till we find this starting bracket. So all the operators between this and this have to come out. So this plus comes out and ABC becomes ABC plus, and multiply is left. So this star was the first star and this one is the second star. So only the first star is left. When the second star comes up, the precedence is matched with the previous one, so they both have equal precedence, so this has to come out. So when this comes out, ABC plus becomes ABC plus multiply, and this second star is pushed into the operator stack. Similarly, when D comes up, D is appended at the postfix string, and the final star comes up in the end. So this expression converts to ABC plus star D star as the postfix notation. We have to convert this one. How to do it? This is the answer. You can see one by one every character is scanned and treated accordingly. By using the algorithm we discussed earlier, the answer has to reach this. You can pause the video and check for yourself. This is the exercise. You have to solve this yourself. This is the solution. I hope you are able to solve and reach this answer. Now we want to evaluate the arithmetic expression. So suppose there is 3 into 4 plus 5 into 6. How to do the infix to reverse Polish notation? 3 is pushed into the postfix string and star is pushed here. 4 comes up here. When this bracket comes up, everything has to pop out till this bracket, so it will become 3 4 star. When plus comes up, it is put into the empty operator stack here. Then this bracket comes up, it is pushed into the stack here. When 5 comes up, it is appended at the postfix string. The star comes up, pushed into the operator stack. 6 comes up, appended at the postfix string. When this bracket comes up, we have to move everything outside till we encounter this bracket, so star is popped out and put here, and the final operator is popped in the end. So the answer will be 3 4 multiply 5 6 multiply plus. So using stack we can evaluate this very easily. When 3 is pushed, then 4 is pushed. When star comes up, the answer is calculated and 12 is pushed into the stack. When 5 comes up, then 6 comes up, then again multiply comes up and 5 and 6 are multiplied. Answer is put as 30. Then the plus comes up, answer is 42. Thank you.